Lesson is about inverse functions, which is a little bit like reversing what a function does, but it can make a graph of its own. The key information has to do, and this is a lot of words on here because it is just information and it's not really an example. But if you can visualize the line y equals x, which of course goes through 0, 0, 1, 1, 2, 2, 3, 3, and so on, that's like a line of reflection. And we just often don't show it, but you kind of visualize that. And what happens to do an inverse is you can trade all of the x and y values. So if you trade x and y values, the moment you do that, you actually have the inverse. But it's not, if you have an equation and you trade x and y values, you will have an inverse equation, but it's probably not in the right form. And we'll practice some of that. So like if you take one graph, here's this blue one is the one you're more familiar with, and it is actually a function, y equals x squared minus 5x, which is just a quadratic. If we reflect that over this y equals x line, it becomes this one that's in this hot pink color. Now, the one in hot pink is not a function. It doesn't pass the vertical line test. So that's the next point that we make down here. When you have an inverse, it's not necessarily a function, even if your original one was a function. So you have to look at whether or not it's a function kind of independently. But there are some ways to know if it's going to be, and that's right down here. If a function is 1 to 1, then its inverse is a function. Now, 1 to 1 really means it not only passes the vertical line test, that's what made it a function, but it also passes a horizontal line test. Okay, it also passes a horizontal line test. So every x has exactly one y, and every y has exactly one x. Suppose we had a list of points, we can say, is this a function? Well, if it's a function, every x goes with only one y. So here, 7 only goes with 8. I don't see anywhere else 7's in this lineup. -2 only goes with 8. We're only checking if x goes with 1y. 3 only goes with -4. And 8 as the next value only goes with -8. So I'm just going to kind of make a chart up here where we can answer some of these questions. First of all, question A, then question B, and I realize this isn't going to make sense right now, but then we're going to put question D. Is it 1 to 1? That means that we also need to check it the other direction. Every y can only go with one x. -8 only goes with 8. -4 only goes with 3. But if you look at it right here, we have an 8 listed twice with 2 different x values. So this means it's not 1 to 1. Find the inverse relation. That's part C. You can find the inverse by simply trading out the x and y values. All right, so all I did was reverse those x and y values, and now I have an inverse relation. Is this inverse relation a function? Well, the same thing that kept it from being 1 to 1 is also going to be what means it's not a function. What was the y became the x, so now I have the x is repeated, but this same x goes to 2 different y's, and in a function, every x can only go to one y. So is that a function? No. All right, let's look at the next one. My x values are 0, 5, and -2. I don't have any x values repeated, so certainly each x only goes with one y. So is it a function? Yes. Is it 1 to 1? Well, I've already checked to see if my x's were repeated, so now I'll look at the y's. 1, 6, -4. None of those are repeated, so it's fine that direction also. So it is 1 to 1. For part C, find the inverse. We need to reverse the x and y's. Just trade them out. Is the inverse a function? Yes. Now, how did I know that so quickly? Let me back up to the previous slide for just a minute. If a function is one-to-one, so when I check that one-to-one, if a function is one-to-one, then its inverse is a function. So right here, is it one-to-one? No. Is the inverse a function? No. Is it one-to-one? Yes. Is the inverse a function? Yes. Those answers go together. -1 goes with -1. -3 goes with 4. That is a function. Now going the other direction, 4 goes with -3 and -1 goes with -1. It worked both ways, so it's one-to-one. If this is yes, I already know this one's going to be yes, because if it's one-to-one, its inverse is a function. Now what is the inverse? It's whatever we get when we reverse those x, y values. Even though on this very first point, it ends up being the same thing. Number 4, -1 goes with 3, 2 goes with 5, -3 goes with 5, 2 goes with 0. It is a function. Is it one-to-one? 0 goes with 2, 5 goes with -3, 5 goes with 2. That's a problem. I had the same y go with 2 different x's, which means this one is not one-to-one. Now, if it's not one-to-one, we're not going to have a function when we do an inverse. Doesn't mean we can't find the inverse, though. We find the inverse by just simply reversing the x and y values. That does not look like a 3, does it? That's a little better. And then 0, 2. So we've completed that if we just have a listing of points. When we're looking at graphs, what we really want to do is consider, does it pass both the vertical line test and the horizontal? The fact that it says that it's a function does mean it already passes the vertical line test. To pass means it only hits it at one point. I could visually see this, but I don't even have to. If they tell me it's a function, I know it would pass the vertical line test. Any vertical line I drew here would only hit it at one point. They have actually put a horizontal line here, and we could visualize moving that red or horizontal line up and down anywhere. But here you see that this horizontal line only hits this graph at one point. So this one also passes the horizontal line test, which means this function is one-to-one. So the inverse is also a function. Now this one, though, we have where this horizontal line hits this graph in 2 places. If it hits it anywhere in more than one place, then it fails the horizontal line test. So it's not one-to-one, and the inverse is not a function. So here again, we have only one point. No matter where I slid that, it would only hit it at one point. It is one-to-one, and the inverse is a function. And here you can even see where they've done this one, and it crosses it 3 times. Not one-to-one, inverse is not a function. If we need to sketch the inverse, I'm sure if you've watching this one, you've probably watched enough to know it's very difficult for me to graph with this little tablet that I have here. But it won't be too hard for me to put some specific points on there, and then we'll try to connect them. I can look at specific points on my original graph, and again, just reverse those x, y values. So 4, 0 will end up at 0, 4. 3, -1 goes to -1, 3. 0, -2 becomes -2, 0. By the way, any point on that line reflects to itself, because that point would be like -2.5, -2.5. So when we reverse it, it's the same thing. And then this one will become -3, -5. Now we wish I could connect all those into a nice smooth curve. I probably can't, but I am going to sketch it. And what you can see, though, is that it is a reflection across there. Now, each of these points then is the same distance from that line. If you went perpendicular, that is the same distance on the other side of that reflection. So here we'll do this one, 3, 5, 1, 2, -3, 0, and this one reflects to itself at -5, -5. So that's how we know what it's going to look like and where we put our lines to do the inverse. This is some key information because one thing you'll have to do is be able to find the domain and range. And we've done a lot of practice on finding domains. Remember, the only thing that you have to do with the domain is make sure that a denominator does not equal 0 or an even square root is not negative. But the domain of one of these becomes the range of the other and vice versa. Those are the two key points here. Now, when we're looking at a graph then, if we're looking at the graph, we can probably just identify the domain and range directly from the graph. But if we're looking at the equation, the easier thing to do is to find the domain of each equation and then just apply it to be the range of the other one. Let's look at formulas for an inverse. If a function's 1 to 1 and you want to find the inverse, this is what we're going to do. Now remember, if a function's 1 to 1, its inverse is a function. Not every function's inverse is a function. That's only true if the original is 1 to 1. So we've just got to make sure if it's 1 to 1, then the inverse is a function. If it's not 1 to 1, the inverse is not a function, so you wouldn't do this last part. We would just leave it with a y, unless we know it's a function. And we do read this f inverse. I know it looks like f to the -1, but this is not raising anything to a power. It's just a notation to say this is a function, and it is kind of the reverse of the first one. So we read that f inverse. So now let's find the inverse of these functions. First of all, replace f of x with y. So y equals 2x minus 3. Then interchange the x and y. X equals 2y minus 3. Now that is the inverse. The moment we did that, we have the inverse, but this is what I meant by it's not in the correct form. We want to get y equals. So what I'm going to do next is I'm going to trade places with this 2y and the x, which will mean this is negative 2y, because it became negative, and then negative x minus 3. And now I'm going to divide both sides by -2. I can do that by drawing one big line, or I could do each individual thing. It doesn't so much matter. So y equals, now -1 divided by -2 becomes 1/2. And -3 divided by -2 becomes a positive 3/2. Now a decimal would be fine. This last step, replace y with f inverse. I can do that. I know that this was a function, and this function is 1 to 1. It is true on both of these, so I'm going to say f inverse of x is equal to 1/2 x plus 3/2. Now, if I were to graph those, they would be reflections over that line, y equals x. Okay, so let's do one more. Even though this isn't g of x, we do it the same way. First of all, replace g of x with y. Then trade the x and y's. Now again, this one is my inverse, but it's not in the right form. I'm wanting to get this y by itself. This time I'm going to take this 2 to the left. It doesn't really matter if you're taking things to the left or to the right. So I'm just doing one way, and this one will do the other way. But I still want to finish this by taking the cubed root to undo that cubed. So I have the cubed root of x minus 2 is equal to y. Now, since my first one was 1 to 1, this one's also a function. If you're ever not sure, don't forget, just graph them. Use your graphing calculator and graph them and check it out, okay? And look at that vertical line test and the horizontal line test. So here, instead of f inverse, I'm going to say actually g inverse of x. And then I have the cubed root of x minus 2. Right? And that would be the answer on that one. These are actually the same equations we just did. This one is just written with it all over 2 instead of having that 1/2 x plus 3 over 2. Same thing though. Graph the function its inverse along with the line of reflection. Now, in order to do that line of reflection, I'm actually just going to insert a line here so that you can see it. So now we see I have that line of reflection. What is my graph? This one will be a little bit easier for me because this one is a line. So when I graph that, I know it goes to the y-axis at -3. And then it has a slope of 2. So it's going to go through those 2 points. And now I'm going to, again, this one, since it is a line, I can go back and insert Z, and that is this equation, and I will write that down. So this one is the 2x minus 3. This one, you know, it doesn't look quite the same in this format, but here's something I know. I know this is the inverse. So I can take these original 2 points I found, and I could easily just reverse the xy values to know where this one's going to go, because the inverse of a line is going to be another line. So this point was 0, -3, so I'm going to go over here to -3, 0. This point was 1, -1, so I'll make that -1, 1. So now I again have 2 points that I can put that line through. F of x, or rather f inverse of x, is equal to x plus 3 over 2. Now this one is a curve. I know that the parent function x cubed kind of looks like this. And what this 2 does is it shifts that up 2. So I do know where this one should go. It's just going to be a little bit more difficult since I can't use that shape to draw on here. That point of inflection, that curve, is now going to be up 2. And the point that's typically on the graph 1, 1 is now going to be here, and my other point's going to be here. So I'm not going to be able to do this real well, but I know it's going to go through those points and continue on. So something like that. Now I'm going to take those original points that I knew were on that graph, and I'm going to turn those around. And that's going to let me graph this one without doing any extra plugging in. I mean, you know, you can just work from your original. You don't have to. But so I can go, instead of 0, 2, I can go 2, 0. Instead of the point 1, 3, I can go 3, 1. And then instead of this point here, which was -1, 1, I can go 1, -1. And anything that's on that line is going to hit itself. So I know that this one, that's my curve kind of. And again, we wish I could do this beautifully, but it's going to look something like that. Here's our next thing. Find the domain and range of each. I could have done this without even graphing because I know how to find domain. And so let me just then say over here, the domain of this, since it's a line, the domain was -infinity to infinity. But the moment I know that, I can take that over to this one and say the range of this one is -infinity to infinity. The domain of one is the range of the other. So then I would look at this function and say, well, there is a fraction, but there's no way that's going to be 0 on the bottom. and there's no even root, so the domain of this one is negative infinity to infinity. And of course, if that's the domain of that, then the range of the other one is the same thing. Let's do that again here. When I look at this one, there's no denominator and there's no even root. Negative infinity to infinity. And that is my domain, which immediately means on my other function, it's the range. Now looking at this one, there's no denominator and there is a root, but it's an odd root. It's not an even root. So I don't have any problem. So the domain, negative infinity to infinity, which means the range of the first one is negative infinity to infinity. I'm not saying that they'll always be to infinity, but I'm just saying focus on what you know about finding domain. A denominator cannot equal 0 and an even root cannot be negative. When two functions are inverses, then when you do a composite, you plug one of them into the other one, you get x. But here's kind of the thing that many students would get frustrated by. You want to be asked to show that, and you're not just supposed to say, well, it equals x. It does equal x because they're inverses, but you actually have to do the work and do little steps. Now, I really recommend that you do this work on scratch paper before you try to do it on a homework problem, because on a homework problem, when they give it to you, they're likely to just give you fill in the blanks, and reading part of it and then having blank show up as a part of it can be really confusing, but it's easier if you can match what they're putting with what you've got. So here, if I want to do f of f inverse, then I look at my f function as holding the place, so that'll be 2 times something minus 3. What am I supposed to put in that blank? F inverse of x. Now, I'm going to do that again, but f inverse of x will actually fill in. So f inverse is x plus 3 over 2. Now, one step at a time. I know it's going to equal x, but you're supposed to show it. What happens next is that the 2's cancel, and we get x plus 3 minus 3. Now, I really kind of want to cancel out those 2's visually for you, but yet when you are working on homework, that's not necessarily going to be the case. You can't put a number and then put a line through it, you know, on your online stuff. Then we go here, and we get the x plus 3 minus 3 equals x. And that one is done. When I'm in a classroom and I do this, it's so much easier for me to write. This is always plenty of room for me to do this both ways. But in this particular case, you know, it's clearly I took up all that room. So what I'm going to do is we're going to start again, and I'm going to go the other direction and get f inverse of f of x. That means I'm going to take this f inverse function as my placeholder. So it's going to be something plus 3 over 2, and the something here is going to be f of x. Now f of x is 2x minus 3, and that's what I'm replacing it with there. Now, order of operations says you've got to do grouping symbols, and numerators are considered grouping symbols. So it does matter the order you do this. This is what's got to go next. That would simplify to 2x. I don't know if you can hear the other stuff going on in the background here, but it's kind of distracting to me. And now then the 2's would cancel, and we get x. The explain part would be anything about how we did that math, but you're kind of hearing me explain it as we go. So again, we're supposed to do this one both directions. So this one will say g of g inverse of x will equal g inverse of x cubed plus 2, which will equal the cubed root of x minus 2 cubed plus 2. Now the cubed is what undoes each other, the cubed root and the cubed. So we end up with x minus 2 plus 2, which equals x. G inverse of g of x would be the cubed root of g of x minus 2, which will be the cubed root of x cubed plus 2 minus 2, which will be the cubed root of x cubed, which equals x. What you put into one, you get out of the other one. And by the way, let me back that up to a couple of concepts back here. When you're finding the inverse, if you want to make sure you've done it right, one thing you can do is plug a number into your first one and then plug the answer back into this, and it should do a complete cycle. For example, if I plug 4 in here, 4 times 2 is 8, and 8 minus 3 is 5. So I plugged in a 4 and I got out a 5. Well, you can plug in the 5 over here. Half of 5 is 5 over 2. 5 over 2 plus 3 over 2 is 8 over 2, which equals 4. So on the first one, I plugged in a 4, I got out a 5. On the second one, I plugged in a 5 and got out a 4. That can kind of give you some reassurance that you've done the math right, because it really does reverse those x and y values, and that's why we get that answer back out of it. Okay, now when a function isn't one-to-one, it doesn't mean they won't use it to find an inverse and make the inverse a function. What happens is that they will simply limit the domain. So if you look at this very first one, it does say give the domain and range of each. And I don't care if you look at the equation or just look at the way it's written, but the domain of this one is negative infinity to infinity. And the range of this one, it starts here at negative 2 and goes up. That should be a closed parentheses, a bracket. I gotta go change that. The range is negative 2 to infinity. But that is not one-to-one because it fails that horizontal line test. So if we find the inverse of it, it's not going to be a function. And in fact, that is that very first thing right here I essentially did. You know, we took a quadratic that was open and up. The inverse of it right here is not a function because it fails the vertical line test. So what we can do is pretend that you only have this section. How do you do that? Limit the domain. This equation here and this one in the second graph is the same. But this one has the domain limited. Over here, the domain for this green one, still looking at the green one, since it said x is greater than or equal to 0, it starts at 0 and goes to infinity. Now the range of this one actually remains unchanged. It goes from negative 2 up. But they've limited the domain so that when we do the inverse is also a function. So this is the inverse. You can get the domain directly from the equation, or I can simply use the fact that I know what was the range is now the domain. And you can see it graphically also. It starts here at negative 2 and it goes to the right. What was the domain of the other one is now the range of this one. So if you're looking at y values, it goes from 0 up. So that's one of the things that you'll also look at within the homework. If they have a domain note put there, make sure that you focus on just that part. so that you can look at the part of the graph that you're wanting to look like. So if they take a function that isn't one-to-one, they can limit the domain, and then it'll be one-to-one, and that way the inverse will be a function. Okay, that finishes up this lesson. If you have any questions, get in touch with me. Email me. Use the Ask the Instructor. Thanks.